Hey everybody, welcome to Algo Expert. In this video, we're going to cover the question of validating a subsequence. This is a pretty easy and straightforward question, but it is an interesting one, mainly because it deals with a concept that's very popular in coding interviews, and especially in some of the harder coding interview questions that we've got right here on Algo Expert. And that concept is the concept of a subsequence. What is a subsequence? Well, it's a concept that stems from mathematics, and here I'll actually read off the definition of a subsequence from Wikipedia, because I think it's a pretty good definition. In mathematics, a subsequence is a sequence that can be derived from another sequence by deleting some or no elements without changing the order of the remaining elements. So for example, if you take a look at the array that I've got in front of me here, the one that starts with 5 and that ends with 10, this is an array of integers, so it's a sequence of integers. And if you were to remove some of the integers from this sequence, like for example, if you were to remove the integer 22, or maybe if you were to remove none of the integers, maybe you didn't remove 22, the remaining elements would be a subsequence of the original sequence. And so this question gives us two arrays of integers, and we're told that they're non-empty, and it wants us to write a function that is going to determine whether or not the second array is a valid subsequence of the first one. So for example here, we have to determine whether or not this array is a valid subsequence of this array. And another way to think about subsequences when we're dealing with arrays is, in order for an array to be a valid subsequence of another array, all of the integers in the potential subsequence have to not only appear in the original array, but they also have to appear in the same order. They don't necessarily have to be adjacent. As you can see here, the numbers 1, 6, -1, and 10 do appear in this array, but they're not adjacent. 1 is here, 6 is here, we've got a couple of integers in between them, then here we've got 8 in between -1 and 10, but they do appear in the original array, and they appear in the same order. They go from 1 to 6 to -1 to 10, 1 to 6 to -1 to 10. And so if we were to call our function, or the function that we have to write, passing in these two arrays, the output of our function would be true because this array is indeed a valid subsequence of this array. So how do we solve this problem? Well, the first thing that we should realize is that we're going to have to traverse both arrays that we're given. We're going to have to traverse the potential subsequence because that's the thing that we're looking for. We're looking to see if this sequence appears in the first array. So we're definitely going to have to traverse our entire second array here just because we have to know what integers we're looking for in the first array. And then we're also going to have to traverse our entire main array because our sequence could basically be located anywhere in the main array. In other words, the first element in our sequence could very well be the first element in our main array, and the last element in our sequence could very well be the last element in our main array. And in this case, it actually is. 10 is indeed the last element in our main array. So we're likely going to have to traverse the entire array. We might be able to stop early when we're traversing our array if we've found our entire subsequence already. But the point is, the logic of our algorithm will likely involve traversing both of these arrays. Now the question becomes, how do we want to traverse them? How do we actually find these numbers and in this order in the main array? Well, one way to think about it is that because the order of the elements in a subsequence and in the original sequence matters, that means that at the very beginning, when we're just starting to look for our potential subsequence, we're really looking for the first element in the potential subsequence. We're not looking for 6, we're not looking for -1, we're not looking for 10, we're looking for 1. Because if we can't find 1, or if we find other elements before finding 1, that doesn't matter, right? A subsequence cares about order. So we're really looking for the first element, which is 1. So what we're going to do is we're going to initialize a pointer underneath the first element of our subsequence, or a potential subsequence, and we're going to say, let's traverse our main array until we find this first element that our pointer is pointing to. And so we're going to put another pointer underneath the first element in our main array. And here, as you might imagine, when we're actually going to write the code for this algorithm, this might be a simple for loop or a simple while loop. But the point is, we're iterating through this array by looking at elements and seeing if we find the first element in our potential subsequence. So here we've got a 5. Is 5 equal to 1? No, it's not. So what we're going to do is we're just going to move our pointer to the next element. We're going to move along in our first array until we find this first element from our potential subsequence. Now it turns out here that the second element is the one we're looking for. This is a 1, and the element that we're looking for is 1. So at this point, what we do is we say, okay, we've found the first element in our potential subsequence. Now we need to look for the second element. We need to look for the number 6. So what we're going to do is we're going to move our pointer in our potential subsequence to the next element. So the pointer now points to 6. And we're going to move our pointer in our main sequence forward. And the reason we're moving forward and we don't have to go back or anything is because, once again, order matters. We found the first element in our subsequence here. That means that any future elements that we're looking to find them after this element. We don't want to go back. We don't want to stay here, obviously. We want to keep going forward. So we're going to move along forward here. And now we're going to do the same thing. We're going to compare the element that we're at in our main array to the element that our pointer in our potential subsequence is pointing at and see if they match. Is 22 equal to 6? No, it's not. So we're going to move forward to 25. Is 25 equal to 6? No, it's not. So we're going to keep moving forward. Is 6 equal to 6? Yes, it is. We've got a match. So at this point, we do exactly what we did when we found the first element here with the 2 1s. We move the pointer in our subsequence forward. So this is now going to point to -1. And then we keep moving along in our main array. So here, we're now going to be under the -1. It turns out that we've got another match immediately. -1 is equal to -1. So now we can move this pointer along to the right and move this pointer along to the right. And to clarify here, what we're effectively saying is that we have found 1, 6, and -1 in this order, not necessarily adjacent, but in this order in the main array, right? And now we're looking for 10, which is the next number in our potential subsequence, and it happens to be the last number. So is 10 equal to 8? No, it's not. Then we move this pointer to the next element, which is 10. And at this point, 10 is equal to 10. So we move our pointer here in the subsequence. We move it forward, and we realize that we are past the bound of our subsequence. There are no more elements here. So we can basically stop the algorithm. And here, this is sort of what I hinted at earlier. We could have had more elements in the main array. We could have had maybe 11 here. We could have had another number, 7. But the point is, we wouldn't have had to keep on going to the 11 or to the 7 because we've finished traversing through our entire subsequence. We found the entire subsequence, so we can stop early. And so that's our algorithm. The algorithm has us traverse both arrays that were given simultaneously, and we're effectively moving forward in the main array without stopping. The only thing that we do is at every point or at every element, we check if that element matches the current element that we're looking for in the subsequence. And in the subsequence, we only move forward when we find a match. Until we find a match for the current element that we're at, we don't move forward in the subsequence. We only move forward in the main array. So as far as complexity analysis goes, let's start with the time complexity. The time complexity of this algorithm is going to be O of n time, where n is the length of the main array. The reason it's O of n time is because we're going to have to traverse through the entire main array. Like we said, we iterate through it without stopping, and all that we do is we check if there's a match with the current element, like for instance, the number 10 here, and the element that we're at in the subsequence. The comparison of the numbers is a constant time operation. Now you might say, but wait a second, sometimes we're going to stop early once we've found the entire subsequence. But that's only going to be in certain cases. It's only going to be if the subsequence ends before the end of the main array, Like here, when we added 11 and 7, yeah, we didn't traverse through the entire main array. We said we could stop at 10 because we found the entire subsequence, but still we had to traverse through the majority of the array. It's not like we only traversed through 4 elements. That would only happen if the subsequence were at the very beginning of the main array. But also, sometimes the subsequence is going to take up the entire main array. Like for instance, before, when we didn't have 11 and 7, when we only had the 10 here at the end, this subsequence had us go all the way to the end, and that's where we found the last element. And also, if the subsequence isn't contained in the main array, like imagine here, instead of having these numbers, we just had the number, 23, we would have to iterate through the entire array to see that 23 is not contained in it. So all that to say, the time complexity is best described here as O of n, where n is the length of the main array, even though there will be a few cases where we will do fewer than n iterations or n operations. Now, as far as the space complexity is going to be constant, so it'll be O of 1, and the reason it's constant is because we're not storing anything extra except for maybe a couple of pointers for our position in the respective arrays. But we're not storing any other big variables or big pieces of data, and more specifically, we're not storing anything that is going to increase in size with respect to the size of the 2 inputs. So with that, let's jump into the code walkthrough to see what this looks like in code. All right, so we've got our validate subsequence function defined. It takes in 2 non-empty arrays of integers, where the second array is a potential subsequence of the first array. And we're actually going to cover 2 code solutions here. They both have the same overarching logic, the logic that we covered in the conceptual overview of this video, but the first solution is going to use a while loop to traverse through both arrays in tandem, and is going to keep track of the positions that we're at in both arrays, whereas the second solution is going to use a for loop to traverse through the main array, and is going to keep track of our position only in the second array. So let's jump into the first solution, the one with the while loop. For this solution, like I said, we're going to need to keep track of our position in both arrays. So we're going to declare our array IDX, which is going to be initialized to 0, and this is going to be our position in the main array. And then we're going to have our sequence IDX, also initialized to 0, our position in the sequence array. And our while loop is basically going to perform some operations. We'll cover the operations in a second, so long as we are in bounds of both the main array and the sequence array. So while our array IDX is smaller than the length of our array, and while our sequence IDX is smaller than the len of our sequence, we're going to perform some stuff. What are we going to perform? What are we going to do? Well, we're looking to see if the element that we are at in the main array is equal to the element that we're at in the sequence array, right? We're specifically looking to find or to match the current element in the sequence. So we're going to say if our array at r IDX is equal to our sequence at sequence IDX, if that's the case, then we found our current element in the sequence, and we're going to move our position in the sequence forward by 1. So we're going to increment our sequence IDX by 1. And then regardless of whether this condition is true, so regardless of whether or not we have a match between our current number in the main array and in the sequence array, we are going to keep moving forward in the main array. So regardless of this condition, we are going to increment our array IDX by 1. And that means that we're going to keep moving along in the main array, and in the sequence array, we'll move along only if we found a match. Eventually, we're going to break out of this while loop, either because we are going to have traversed the entire sequence, or because we're going to have traversed the entire array, or both. And in that case, we're going to return whether or not we have found a valid subsequence. How do we know that? Well, if we've traversed through the entire sequence by the end of this while loop, then we found a valid subsequence, because that means that we will have hit and satisfied this if condition here m times, where m is the length of the sequence, and therefore we will have matched all elements in the sequence, and we will have a valid subsequence. So we will only have a valid subsequence if the sequence IDX is equal to the length of the sequence. if we're ever at a point here after this while loop where the sequence IDX is smaller than the length of the sequence, either we're still at the very beginning, or maybe even we're at the very last element. Maybe we're at len of sequence -1 here. Well, if that's the case, we clearly didn't find all of the sequence elements in the main array, and we do not have a valid subsequence. So here we want to return sequence IDX is equal to the length of the sequence. And so like I said in the conceptual overview of this video, this algorithm is going to run in O of n time, where n is the length of our main array, and it's going to run in O of 1 space. And you can see the space complexity very clearly, right? All that we store are these two variables here, nothing that increases with the size of the inputs. And as far as the time complexity, you can see here that we are going through the entire array with this while loop. And once we reach the end, we break out of it and we're done. We might break early if the sequence is smaller, but we're not sure. And there are many times when, for instance, we're not going to have a valid subsequence, when we're going to have to go through the end of the array. So the most accurate way of describing this time complexity is going to be O of n, where n is the length of the array. On average, or in the worst case, it's going to be O of n. So this is the solution that uses a while loop. Now let's cover the solution with a for loop. So we'll copy the code. Well, I guess we'll comment it out first. We'll copy the code and delete most of it. The one thing that we'll keep is the sequence IDX initialized to 0, because we're still going to keep track of our position in the sequence with this pointer. But instead of a while loop with the array IDX pointer, we're just going to do a for loop through the array. So we'll say for value in our array. And here we're going to do a similar check as we had here on line 6 with the if statement. We're going to say if our sequence at the sequence IDX is equal to our value, then we have a match, right? It's the same sort of logic as here. We have a match, and what do we want to do? We want to increase our sequence IDX. We'll say sequence IDX plus equal to 1. However, the one thing that we want to do here, since we don't have our while loop that's going to break if we're out of bounds with the sequence, is we want to add this condition inside of our for loop. So before we actually do this if statement here, which would probably cause an error because we might be accessing something out of bounds, we want to have this condition that is going to say, if our sequence IDX is equal to the length of the sequence here, then we break, right? We break out of our for loop. So we're essentially mimicking this while loop condition here. And then if we break out of our for loop, we just return the same thing. Sequence IDX is equal to the length of the sequence. And of course here, you don't even need to break. You could just return true in this case, because if our sequence IDX is equal to the len of the sequence, then we've got a valid subsequence, but we're going to check this here at the very end anyway. So I just like to break here. Up to you. As far as the complexity analysis for this solution, it's going to be identical to the first one. So I'm just going to go ahead and copy that here. And the reason it's identical is because we're doing the same logic, right? We're only storing one variable here with our index. We're iterating through our array here and keeping track of the value. We're not storing anything with respect to the size of the input. And as far as the time complexity, we're really just doing a for loop through the array. So it's going to be O of n time. We might break early, but we don't really know that. On average, or in the worst case, we won't break early, and that's why it's O of n time. So with that, I hope that you found this video informative, and I'll see you in the next one.